Hi guys, this is Mrs. Gastler, and in this video we're going to talk about interpreting graphs, and we've got some notes here that we're going to look at together, and then you're going to do some practice about this. And we can read this together, but I know you guys have eyes and you can read, and if you can't or that is a struggle for you, you can always come talk to me about that. And I'm just going to look at these graphs and we're going to talk about what this means. So these are linear relationships, and there's two different kinds here. And we'll talk about some of the other graphs that you see on that chart that's on a yellow poster in the room somewhere. First off, when we have a straight line, notice that it's a straight line. It doesn't curve, it's straight. It could also be flat. Flat lines look like this. This is a flat line, okay? A flat line means something in particular. This means the slope equals 0, and that's a special case of a straight line. When we see this happening, what we have here is a direct relationship, and what we'd say is we would say that y is directly proportional to whatever x is. And that means that we have a linear relationship. So it is a linear relationship. And that means that this format right here, which you might have seen in math class, is y equals mx. Or in the case down here, y equals mx plus b, is the format of an equation that would describe this line. And we just need to figure out what m is, okay? But the reason we use k instead of m is because while in math class, can you see where I'm writing? In math class, m does mean slope, and you can find the slope of a line exactly the same in physics class as you would in math. In fact, all math works the same in physics as it does in math, okay? It's the same math. But in physics class, m means mass. And that's why we don't use it, okay? That's why we use k instead. K is actually something else in physics class, but we don't use it except for this one time, whereas mass is everywhere. Mass is in almost everything that we use. We're going to have mass show up in every single unit that we're in. And so if we used m for our slope in these lines, we might get confused, and we don't want to think it's the mass. In some of our lines, the slope might actually be the mass. And that would be great. In fact, that would actually be really cool if the slope happened to be the mass of whatever we're talking about. But if it's not, then we need to call it something else. And so we use k as our constant. So k is just a constant that happens to be the slope of the line, and only in a direct relationship like this. Okay, directly proportional to. Okay, so that's what we would say for linear relationships. So if you have data on a graph and it looks like a line, you would draw a best fit line, and then you would be able to find your line by some means. If you were asked to find a slope, you would find some points on your line where it actually crosses the grid. This one actually doesn't seem to cross the grid anywhere. Kind of like there. We might look for some halfway points, maybe there. And we would actually, we'll have to do that at some point in time. This one looks like it's got a spot right there. I don't actually see any other ones on this one either, but it looks like it might go through 0, 0, and so I might use those to find the slope of this line. The next kind of relationships we're going to look at are inverse relationships, and so this one is actually kind of the opposite. We're still using that k as a constant. K is just a constant that represents something about the line. In fact, we'll be using Microsoft Excel to be thinking about what that k represents on occasion, but in this situation we have an inverse relationship, so we would say that y is inversely proportional to x. This is the whole when one goes up, the other goes down kind of relationship. If I increase x, y decreases. You can see that on that yellow poster as well. For this one, we would just say the same thing, but we would say y is inversely proportional to x squared, okay? And you might notice that the difference here is that this one is more of a gradual drop-off, and this is a sharp drop-off. And really the only way to know on your own data is by plugging it into a graphical analysis software such as Microsoft Excel, or a program called Graphical Analysis that I don't think we have access to. Logger Pro can do this one as well. and you'll either get a really good fit for this one or a better fit for this one. And it's kind of like a corner right here, and you'll see that as long as you have enough data points. So you need like 5 or more data points to really be able to see whether it's inverse or inverse square on this kind of relationship. Okay. But those are some pretty cool ones. We'll see both of those this year in AP Physics. Okay. The next kind of relationships are called exponential relationships, and you might learn about exponential relationships, and they're e to the something, but that's not what we're talking about here. We're really just talking about it includes an exponent, but it's not 1 over. Okay, it includes an exponent. That's really all we mean. So you'll see here, this is y equals kx squared. So this one is a parabola here. And so y is proportional to x squared. And here we've got y squared is proportional to x. And so that's kind of the opposite of this one. We've just kind of flipped it over. This one, sometimes we call this one a square root relationship. And that's okay. That just means that we've got an exponent in our relationship. We don't mean that they're actually exponential or like an exponential decay, something like that. It's a little bit different than e to the x or a logarithmic function, which in advanced physics you might actually run into, and that's okay. Now, the real reason we use graphs is because sometimes we need to either predict what's going to happen next, or we need to predict within our values. And so the two things that we're doing are interpolation and extrapolation. And when you take the ACT, you might have to do both of those. So let's say you have some data, and this is where your data is, and you have been asked to predict something that is right inside here, okay? And so you have to find where that is. So maybe you're given this point and you have to figure out what this is, okay? But it's inside your data. That would be interpolation, okay? Inter means inside or between, okay? And so this would be interpolation because it's inside of interpolation. Sometimes I feel like a picture helps me understand things a little bit better. If on the other side I have to expand my data, so my line looks like it's going to keep doing this. So if I want to know what's going to happen way the heck over here, and I have to extend my line out to see where that's going to be, I have just extrapolated. Okay, so this would be extrapolation. Extrapolation, running out of room there. Okay, so when I'm looking outside of my data, that's what's going to be. That's what I'm going to be looking at. So if I'm taking my small scale experiment and I'm expanding it to a larger scale to think about what's going to be happening, I'm using extrapolation. Okay, so those are the two words there. Extra, outside. Extraterrestrial is a word that comes from the same thing, okay? So those are two word parts there that can help you think about what those two things mean. In the practice, you're going to be graphing and determining what kind of relationship you're looking at. Sometimes it's not easy to see from the data, and sometimes it is. And you're also going to be doing some interpolation and extrapolation, okay? And drawing it on the graph, kind of like this, okay? If you have any questions about any of this, make sure you ask your teacher. You're going to get a lot of practice doing this in class. Thanks for watching.